So for the next talk on Chaos West stage, we go into the fast track, into the shorter talks, and nevertheless, this will be an interesting insight into something that has a lot of implications for transparency in systems, and that's why the talk is called System Transparency, and it will be held by Kai, and Kai is a hacker from Bochum, and I give you the stage.
Hey, so the 2020 is only a few days away, and while we do not have flying cars or sex robots, we do live in a dystopian nightmare. A dystopian nightmare where our computing is more and more controlled by unaccountable Silicon Valley companies. There's no turning back. The centralization of computing and data will only continue into the cloud, because this makes things cheaper and also allows us to do things we couldn't do before. 30 years ago, we were faced with a similar threat. Proprietary software stifled competition and prevented extension of software. The result was the free software movement that had openness and freedom as its core tenets. Today, we recognize that open and free software is a superior software development model. Ironically, free software won't help us this time, because free software is one of the reasons why these cloud companies as a business model work so well. What we need to do instead is to take one of the core ideas of free software, transparency for the user, and reimagine that for the world of PaaS and SaaS. So, I'm Kai, and I'm a hacker from Bochum, and today I want to tell you about the System Transparency project here. And of course, nothing I will tell you here is just my idea. I'm merely here to tell you about it, and the System Transparency project mostly grew out of the open source firmware community you can find here right behind the stage. So, System Transparency has the goal of making the software running on a remote server that processes third-party data inspectable by that particular third party. To do that, we proposed 7 concepts. The first one being that we need some kind of provisioning ritual, because these servers are hard to get a handle by, right? So we have this intransparent cloud, and what we need to do is give every one of these servers a unique platform identity, so we can decompose this cloud into individual servers, which allows us then to make specific statements about specific servers. Second, we need to make sure that the firmware, the first and most privileged code that's executed on the machine, is known to us and can't be changed by an attacker. To do that, we need to have some kind of integrity protection for the firmware running on the machine. Third, because we still have physical attackers, we need to make sure that the machine is somehow tamper resistant, or at least tamper evident, so we can see when at least attackers try to change the firmware, and thus try to attack the system. Then we need some kind of platform attestation, meaning that before I connect to a machine, I want to make sure that the software it runs and the identity it has is known to me before I send it my data, right? Otherwise, I have the problem that my data may be handled by software I have no idea about and maybe is abused. And because all of this platform attestation and also the integrity protection of the firmware is done on the binaries, we can only expect the source code. We need to establish some strong link between the source code we were able to inspect and the binary that's actually handled by these platform attestation mechanisms. Reproducible builds does exactly that, right? Because I can recompile the source code I have inspected, and I will get the same binary that's running on the machine. Then we need to limit the system access, because even if we have integrity-protected firmware and we know everything that has been executed as part of the boot, we can still have a malicious administrator logging into the system and changing things in ways we can't control. So we need to limit the system access. We need to have some kind of immutable infrastructure. And lastly, we need a transparency log for all the software running on a particular server, so we can monitor not only the current, but also the past actions of platform owners, so we can audit them. This is somehow like the certificate transparency mechanisms we have with PKI. So system transparency is not just a bunch of concepts. It's an actually working implementation. For that, we use the Supermicro X11 SSH TF, which is a mid-range server board from Supermicro. It has up to 4 cores, 64 gigabytes of RAM, 2 10 gigabit NICs, and PCI Express. You can get these boards for less than €1,000 on the market, and these can be used to do everything I will tell you now. So in order to have some kind of unique platform identity, we use a chip that's already soldered onto this mainboard called a TPM. The TPM contains a unique certificate and a private key for that certificate that's inside this extra chip and can never leave it. We can use that to use our unique platform identity. And also, it allows us to record what's booted, what's executed as part of the boot chain. So the TPM has a special feature where it records the cryptographic checksum of all the code that's executed as part of the boot process. We can then later read that out and verify that, okay, it booted exactly what we expected, including the operating system. Our X11 runs open source firmware. So we have a stack of core boot and Linux boot, core boot doing the early initialization of the hardware, and then later executing Linux boot, which boots into the operating system. We use a bootloader based on Linux boot called stboot to do all the boot process, especially fetching a new operating system image from the network, verifying it, and then booting into it. And because we use core boot, and core boot can be built reproducibly, we can use that as our secure initial state we boot from. Everybody, not only the platform owner, can fetch the source code, the core boot source code we run on the machine, compile it, and verify that this is the bit exact copy of that what has been recorded by the TPM as part of the boot process. So we can make sure that this is exactly what a platform owner is supposed to run on a machine. Yeah, as I said, we have a special bootloader called stboot that does all the booting after the initial hardware setup. We do a boot over HTTPS. We then do a signature verification and some other stuff, and then boot into the operating system. We can boot pretty much any open source operating system. So not only our firmware, but also our operating system can be built reproducibly. In this case, we built the kernel, the initial RAM disk, and the complete operating system to one blob that is always the bit exact copy of what everybody else has compiled. We then sign that, and the platform owner signs this hash, signs the hash of this blob. We can also configure stboot in a way that we require more than one signature. So, for example, if the platform owner has 5 administrators, stboot can be configured in a way that at least 3 of them has to sign the image before it's then booted. While that's all nice, the core idea of system transparency is that everybody else, right, users, can verify what's running on the system. And to do that, we also require the platform owner to request a new X509 certificate for every operating system image he wants to deploy on a server fleet. This certificate will contain the hash of the operating system image as part of the common name. And because the CA that issues the certificate is working with the certificate transparency lock, we have then the hash of the operating system image inside the append-only certificate transparency lock that's run by Cloudflare. And now we have an open append-only and public certificate transparency lock of all the current and past operating system images that have been deployed on a particular system. And because stboot, before it boots, checks that the certificate transparency lock contains such a certificate, you can make sure that everything that boots on a particular server has been verified by us. So, in a nutshell, system transparency partitions the intransparent cloud of servers into a set of individual servers that have unique and has unique platform identities, which allows us to do specific statements about specific servers, right? Because we are still connecting to specific servers. System transparency also makes all the code running on a particular server visible to the users, which means that we force bad actors to lie about very specific things. So for example, if you have a VPN provider and they tell you, well, we don't keep any logs, in order to verify that, you have to first figure out, okay, what does keeping logs means? With system transparency, you can just get their operating system image, get the source code, and inspect the source code and decide whether you consider their implementation of a VPN privacy respecting. You can then compile that and verify that you get the exact copy of that, what has been inserted in the certificate transparency log, and then can verify that, okay, the thing I'm connecting to now does not have any kind of backdoors. Now, a malicious VPN provider has to lie about a very specific thing, which is this particular server with this particular unique ID runs this particular operating system image with this particular hash, right? And the more concrete these lies have to become, the easier it is to capture them. No, sorry. Also, system transparency provides a public log of everything that has been done also in the past by the operating system provider. This means that we can audit any provider more thoroughly than what we could do before, right? Because we can check, okay, what happens before we have used this machine. This also means that every platform owner, every provider has to commit publicly and irrevocably to every operating system image before it is deployed on a machine, which means we, as a concerned user, can monitor the certificate transparency log, see for new operating system images, and then verify them. And when we decide, okay, there are some changes we don't like, we can either stop using their service or alert the public. And lastly, system transparency works with open source firmware, bootloaders, and operating systems. And this is important because this is the mechanism that actually allows us to inspect the source code and somehow closes the power gap between platform providers and platform users. So, what's the future? In the dystopian nightmare of 2020, we will hope to grow this ST-boot and system transparency project into a more major open source project, which means hopefully that the ST-boot bootloader is maintained, we have better documentation, we have more features. Also, we want to support more hardware. So currently we support everything that CoBoot and ST-boot supports, which isn't that much. So we want to grow, especially in the x86 market, to support more servers that actually used in practice. Speaking of practice, we actually want to have a first transparent server running in production by the end of next year, to prove to the public that this idea can actually work with real VPN providers, for example. We also we're piggybacking on the certificate transparency effort. We want to change that and develop our own certificate transparency log. For example, this software transparency log can include then, for example, the source code of the thing we want to verify instead of just a pointer. And lastly, currently we're depending on the TPM, which runs most of the time proprietary software. We want to change that and figure out, okay, how we can use open trust anchors, for example, the Open Titan project, or something based on RISC-V or something else. And lastly, we of course want to invite you to join our effort. So in case you are interested in open source firmware and the system transparency project, you may want to check us out. We are just right behind the corner. The open source firmware assembly we are always happy to help you, and happy to help you with any hardware you have there, especially if it's about system transparency. And so if you have a question now, you can either ask me or go to our website where we have all the documentation ready. And if you want just to talk to us in person, you can go to the open source firmware assembly and catch us there. Thank you.
Thank you, Kai, for a very concise talk. So we have a bit of time for questions. You can queue up at the microphones, or we can see if there are internet questions. No internet questions. Are there on-site questions? Come on. Anyway, if you feel like, oh, we have a question from the internet.
Yeah, the internet thanks you for the talk and wants to know what about mobile phones? Now we can unlock bootloader, but no,
sorry, I don't understand. Can you repeat it?
now we can unlock bootloader, but not to relog again. Sorry, I should have read that earlier. Sorry, give me a second.
Okay.
Okay. Maybe in the meantime, you are queuing up? Okay.
Yes. Thank you for the great talk, a very interesting project. I've got one question. One is, can you make sure you learn about any admin interaction with the cloud server in the end? Because that's one major concern I would have if I run it on a provider hardware.
Right. So first, you can inspect the operating system image, right? And you can, when you see, okay, there's an OpenSSH server running, you know that the system isn't secure, strictly secure, right? Because everybody can log in and change everything. What we imagine is that either you forbid any SSH access whatsoever, which makes debugging a bit complicated. Then you would have to, for every change you want to do in the server, you have to deploy a new operating system image, right? Which makes things very transparent, but also very annoying. What we can imagine is that instead of dropping into Bash, for example, you could have a restricted shell that drops into some script that does allow you some things, like restart a server, get some log output or whatever. This, of course, only includes what the machine itself can do, right? If you're running in a hypervisor, you have maybe other ways to look into the system. This is the classic problem you have with trusted computing is you need to control everything, or you need to say, okay, my hypervisor or my hardware running on it is secure, right? This is a problem we can't really solve.
Can I have a follow-up question?
Yes.
Sure.
Concise question.
Yes, sure. From what you said, I could imagine that there is a big company side interest, specifically like from large infrastructure companies from Europe. Is that the case, or?
We try to convince some of them, but I mean, if you go to Google or Amazon and tell them, hey, I have this great idea about system transparency, it's hard to get in there, right? Yes, we know of some companies that do something similar, right? So the ideas we have here, these 7 concepts, they existed somewhere else too, right? And these specific concepts were introduced to us by the Mulvad VPN provider, that they had this idea initially to somehow differentiate themselves from the other VPN providers.
Okay. Signal Angel. Could you repeat your internet question?
No, sorry.
Okay, question is gone. Is there another question from the microphone, or? No? Okay, I think that lands us perfectly at the end of the talk. And as Kai said, you can visit them at their assembly and you can connect with them in any way. And I'm looking forward to next year. And round of applause for him.
Thank you.